The phenomenon of entanglement is one of the most remarkable effects of quantum mechanics and strongly puts our image of the world around us to the test. In this video, the entanglement shall be explained in a simple and understandable way. In doing so, we will completely avoid the corresponding mathematical descriptions and derivations. Instead, we will use illustrative examples and comparisons in the appropriate places to explain the contents. This approach shows that this video isn't aimed at experienced physicists, but at interested non-experts without mathematical and physical knowledge. The key point of the phenomenon of entanglement is that entangled particles are no longer independent of each other. In other words, they cannot be seen as single, separate particles anymore. In classical physics, and thus in our everyday experience, this phenomenon cannot be observed. Entanglement is a phenomenon that occurs only at microscopic objects such as electrons or photons. Physical experiments are often performed to determine the properties, like the mass or the speed, of objects. For our entanglement experiment, the property of the spin of electrons will be important. Therefore, we first need some information about the electron's spin. That leads to the question, what is the spin? Strongly simplified, we can think of the spin of an electron as a rotation. However, this image should not be overstrained by any means. The spin is a purely quantum mechanical property, and there isn't any exact analog to the spin in classical physics. Macroscopic objects, such as a rotating ball, have no spin. Therefore, we should interpret this image this way, that microscopic particles behave in some situations as if they would rotate. For example, one important difference is the speed with which the respective objects can rotate. A ball can rotate at different speeds, but an electron always has the same spin. Thus, the spin of an electron, and also of all other elementary particles, is immutable. In addition, the spin has a considerably bigger importance compared to the rotation of a ball. It belongs to the properties that define a particle. In other words, electrons are electrons because they always have the same properties. And besides, for example, the mass and the electric charge, the spin of an electron is one of these properties. But the exact nature of the spin is not really important to us. It is much more important what follows from the spin. Because the electron is a particle that has a spin, it also has a magnetic field. And the magnetic field of the electron looks like the magnetic field that surrounds a small bar magnet. However, it is not correct to draw the conclusion that the electron is something like a microscopic bar magnet. The electron is a particle that must be described by quantum mechanics and shows significant differences to a classical bar magnet. We will concentrate especially on one of those differences in the context of a very important experiment. A bar magnet, as it is shown here, is called a magnetic dipole. It is called dipole because it has two poles, a north and a south pole. The two magnetic poles are normally marked with colors, with the north pole colored red and the south pole colored green. By the way, we only let our bar magnet rotate here to gain a better impression of the three-dimensional structure of the magnetic field. As the bar magnet is a permanent magnet, it always has a magnetic field, and it doesn't matter whether it is rotating or not. We will always use this bar magnet shown here when we want to demonstrate effects from the field of classical physics. So now we let our bar magnet disappear and replace it with our electron. In this video, we will always symbolize our electrons, as shown here, by blue spheres. However, in the following we will refrain from representing the spin by the rotation of the spheres. The fact that the electron has a magnetic field due to its spin enables us to examine the spin more closely through the magnetic field produced by the spin. For this, we take advantage of the effect that a magnet can be affected by a second magnet. This occurs because a force is acting between two magnets. This force causes two different poles to pull on each other and to repel two poles of the same kind. So north and south poles attract each other, while two north poles or two south poles repel each other. This is used, for example, in a compass. The compass needle is nothing else than a small bar magnet which aligns with the Earth's magnetic field. The Earth's magnetic field is usually referred to as the external magnetic field to distinguish it from the magnetic field of the compass needle. To get further information about the spin of the electron, we will expose our electron to an external inhomogeneous magnetic field and observe how the electron reacts. But before we start our experiment with the electron, we will have a closer look at the external magnetic field to see what it means when a magnetic field is inhomogeneous. First, we see here the simpler case of a homogeneous magnetic field. Homogeneous means that the magnetic field has the same strength everywhere. This is symbolized by magnetic field lines which all have the same distance from each other. If our magnetic field would be stronger, then the magnetic field lines would be closer to each other. Conversely, the field lines would be further apart from each other in a weaker magnetic field. The important point here is that the force that acts on a bar magnet which is located in a magnetic field depends on the strength of that magnetic field. Therefore, the closer the magnetic lines lie together, the greater is the force on a bar magnet in the magnetic field. Now we look at the more important case of an inhomogeneous magnetic field. It is called inhomogeneous because it does not have the same strength everywhere. In this case, the inhomogeneity arises from the shape of the pole shoes between which the magnetic field is formed. In our example here, the field lines at the North Pole lie closer together than the field lines near the South Pole. In contrast to a homogeneous magnetic field, the force on a bar magnet in this magnetic field is now greater at the North Pole than at the South Pole. And exactly this difference in force is the crucial point why we will use an inhomogeneous magnetic field for our experiment. To be able to interpret the measurement results of the coming experiment, we need to look at what happens exactly with a magnet that is under the influence of an external inhomogeneous magnetic field. First, we examine the situation in classical physics, and therefore we use our bar magnet. Since we want to refrain from the mathematical description of the force on the bar magnet, we will instead have a look at the forces on the North Pole, the South Pole, and the bar magnet as a whole. Shortly, we will look at different orientations of the bar magnet. As a result, we will find out that the force acting on the bar magnet exactly depends on these orientations. To represent the force, we will use blue arrows indicating the direction in which the force acts. In addition, the length of the arrows symbolizes the strength of the respective force. So, longer arrows mean a larger force. We will, as seen here, no longer display the magnetic field of the bar magnet and in the following of the electron anymore. It would be annoying if we would display the magnetic field lines of the external magnetic field and the bar magnet or the electron at the same time. With so many field lines, we could hardly see anything. First, we place our bar magnet vertically in the external magnetic field. In this position, the south pole of the bar magnet points to the north pole of the external field and vice versa. The field lines of the external magnetic field lie closer together at the south pole of the bar magnet than at its north pole. Therefore, the attractive force on the south pole of the bar magnet is greater than the attractive force on its north pole. The bar magnet as a whole will be attracted to the north pole of the external magnetic field. The difference of the two forces on the poles of the bar magnet is crucial for this movement. We take the force that acts on the south pole and subtract from it the force that acts on the north pole. The resulting force is the one which moves the bar magnet as a whole. It points in the direction of the north pole of the external magnetic field. This is the reason why our bar magnet is pulled to the north. Let us now look at a different, slightly angled position of the bar magnet. As a result, the south pole of the bar magnet is now located in an area in which the magnetic field lines are not so dense as in the previous case. Therefore, the attractive force on the south pole of the bar magnet is a little weaker than before. At the location of the north pole, the situation is exactly opposed. Here, the field lines are now closer together than in the previous example. The consequence of this is that the difference of the forces has now decreased. The bar magnet as a whole will still be pulled in the direction of the north pole of the external magnetic field, but not as strong as before. Hence, the more horizontal the bar magnet is positioned, the less it is attracted to the north pole of the external magnetic field. The reason for this behavior lies in the difference of the forces on the two poles of the bar magnet. The smaller the angle of the bar magnet, the less its south pole will be pulled to the north, and the more its north pole will be pulled to the south. So the difference of the forces will decrease with decreasing angles. What happens if the bar magnet is positioned exactly horizontal in the external magnetic field? In this case, the field lines of the external magnetic field are equally dense at both poles of the bar magnet. Therefore, the forces on the north and on the south pole are equal. This means that the force difference is zero, and the bar magnet as a whole doesn't move at all. Now we have turned the bar magnet a little bit further to see what happens then. In this case, the field lines of the external magnetic field are closer together at the north pole of the bar magnet than at its south pole. As a result, a small force difference arises, but the resulting force is now pointing to the external south pole. So the whole bar magnet will move towards the south pole of the external magnetic field. And again, the force difference will grow with increasing angles of the bar magnet, just like in the previous case. The maximum is reached again when the bar magnet is positioned vertically in the external magnetic field. But now the magnet moves down to the south pole of the external field. The key point here is that the bar magnet in an external inhomogeneous magnetic field experiences a force whose strength and direction, as shown here, depends on its orientation. Now we know how an object that possesses a magnetic field like a bar magnet behaves in an external inhomogeneous magnetic field according to classical physics. Thus we can return now to our initial task. We wanted to get information about the spin of the electron by exposing it to an external inhomogeneous magnetic field. To solve this task, we now look at one of the most important experiments of quantum mechanics, the Stern-Gerlach experiment. The main part of this experiment is a magnet with an inhomogeneous magnetic field. In front of it, the source that emits a beam of particles is positioned. An assembly of apertures is placed between them to focus the particle beam as narrow as possible. Behind the magnet, a detector screen is located that registers the impacting particles. It is important to mention for this experiment that the particles which leave the source are not prepared in any way. This means that the orientations of the particles are completely arbitrary. Therefore, particles with all possible orientations are located in the particle beam. We will perform the Stern-Gerlach experiment twice. First with our small bar magnets to see the result for the case of classical physics, and then with our electrons to observe the result for the quantum mechanical case. First, we have a look at the classical case. We know that bar magnets are deflected differently while they are in a magnetic field. The strength of the deflection depends on the orientation of the bar magnets relative to the external magnetic field. Therefore, we can observe that the bar magnets are deflected from their original straight trajectory and that the particle beam fans out under the influence of the magnetic field. A line is formed on the detector screen, and exactly this line refers to a behavior of the particles according to classical physics. Now we will perform the Stern-Gerlach experiment with our electrons to see what the result looks like for the quantum mechanical case. However, electrons are not well suited for a real experiment. The reason for this is the fact that they are charged. Charged particles that move through a magnetic field are subject to an additional force, commonly known as the Lorentz Force. This force would deflect our electrons to the side so that they would not hit the detector screen. We will neglect this influence of the Lorentz Force on our electrons, since we are only interested in the basic principle of the Stern-Gerlach experiment. By the way, Stern and Gerlach used silver atoms in the original experiment. Those are uncharged and they have a spin like electrons have due to their inner structure. Opposed to the classical case, it turns out that no line is formed here on the detector screen. So we do not get a continuous distribution of particles. Now the particle beam splits into two partial beams while it is going through the inhomogeneous magnetic field. And on the detector screen, two separate areas show up in which the electrons impact. The question is now, how can this result be explained? Quantum mechanics answer the question this way. Under the influence of an external magnetic field, the spin of a particle can orientate only in certain directions. The external magnetic field, in a sense, forces the particles to decide for a certain orientation. This behavior is called the quantization of angular momentum. In the case of an electron, only two orientations are possible. These are commonly known as spin up and spin down. This behavior is not explainable by means of classical physics. So this experiment shows that the spin is clearly a quantum mechanical property. And the Stern-Gerlach experiment is an experimental proof of the difference between quantum mechanics and classical physics. Therefore, the Stern-Gerlach experiment, in simple terms, constitutes a measurement of the spin of the respective particle. But there is another important aspect in this experiment, except for the quantization of angular momentum. For showing this, we have changed the setup of our experiment so that the source emits only single electrons. And now we determine the number of electrons which hit the two areas on the detector screen. By the fact that now only one electron is always located between the pole shoes of the magnet, we can exclude an interaction of the electrons. What we see is that an equal amount of electrons hit the two areas of the screen. In other words, the probability that an electron hits one of the two areas is 50%. This experiment shows that the probabilities for the two possible states, spin up and spin down, are equal. The Stern-Gerlach experiment is based on an important phenomenon. As mentioned earlier, our source emits particles with all possible spin orientations. In contrast to the classical case, the particles are not deflected here according to their orientation in the external magnetic field. Instead, they enter one of two possible states. Unfortunately, there is no way to predict which of the two states a single electron will enter. We only know that the probability for each of the states is 50%. The actual result for a single electron depends on chance. The situation is, in a sense, similar to the flip of a coin. As we will see later, this phenomenon will turn out as an important aspect of the entanglement. By the way, this is not an isolated phenomenon that only occurs at the Stern-Gerlach experiment. On the contrary, it is characteristic for quantum mechanics, and thus an important difference to classical physics, that the result of an experiment cannot be predicted exactly. In general, quantum mechanics can only make statements about the probability for the outcome of an experiment. Albert Einstein was extremely dissatisfied with this, which he wanted to express with his statement that God does not play dice. In the following, we want to look at the Stern-Gerlach experiment from a quantum mechanical point of view. Thus we can abandon the idea of electrons being small rotating spheres. To do this, we need to deal with an important principle of physics, the superposition principle. The word superposition means overlapping, and the principle of superposition says that physical quantities can overlap under certain circumstances. In quantum mechanics, the principle of superposition means superposition of states. In relation to the Stern-Gerlach experiment, it is about the two possible states of the spin of the electron, spin up and spin down. In the further course of this video, we will characterize these two spin orientations by arrows as shown here. The electron in the state of spin up can be seen on the left side, and on the right side, the electron in the state spin down is shown. Since electrons are not small rotating spheres, these arrows do not stand for their axis of rotation. They symbolize the two possible states. The superposition principle states that a particle at which no measurement has been carried out yet is in superposition of all its possible states simultaneously. This superposition is resolved by a measurement, and the particle enters one of the possible states. But it is unpredictable in which of the possible states the particle will be after the measurement. We can only calculate the probabilities for each state. In the case of the spin of an electron, the calculations show a probability of 50% for the state spin up and of 50% for the state spin down. These values correspond exactly with the data from the Stern-Gerlach experiment. So the source of the Stern-Gerlach experiment does not emit electrons with arbitrarily orientated spins. And as these electrons have not been prepared in any way, which means that their spin has never been measured, they are in a state of superposition. In other words, they have not assumed one of the two possible states before entering the external magnetic field. They are in superposition of these two states. Figuratively speaking, this means that this superposition consists of the two states spin up and spin down at the same time. It is said that the state of an electron before any measurement is indefinite. Perhaps we can illustrate this situation better with a descriptive example. Imagine we would measure the property of color of a liquid. The two possible values of the color would be blue and yellow, corresponding to the two states spin up and spin down. So after the measurement, our liquid would be either blue or yellow. And before the measurement? There it is in a superposition of the two states. And when we mix blue and yellow liquids, we will get a green liquid. That means, before the measurement, our liquid would be green. But green is not one of the two possible results here. It is only a superposition of blue and yellow. In this case, we only have another name for the superposition of the two colors. We call this superposition green. The superposition principle of states is an important principle in quantum mechanics. By the way, in classical physics, the state of an object is always determined. It doesn't matter whether a measurement is carried out or not. A measurement only determines an already existing state in classical physics. Now we have sufficient information by the conclusions from the Stern-Gerlach experiment and the principle of superposition to deal with the quantum mechanical phenomenon of entanglement. For a better understanding, we first have a look at the principal setup of an entanglement experiment. The central element of such an experiment is a source that emits entangled pairs of particles. The exact functioning of the particle source is not of importance for further consideration. It does also not matter whether the emitted particles are atoms, electrons or photons. The basic principle of entanglement always remains the same. For our entanglement experiment, we will assume that our particle source always emits pairs of two electrons which always have opposite spin orientations due to the way they are generated in the source. Furthermore, we need two detectors for our experiment to be able to determine the spin of the two electrons. Our experiment now works as follows. The particles leave the source and hit the detector. Thus we can determine which of the two possible states the two electrons have entered. What is the result of this entanglement experiment? Whenever we get spin up as a result at one detector, then the other detector displays spin down. So we never measure the same spin at both detectors. This result is not surprising. We knew even before that the two electrons must always have opposing spins. At first glance, we only confirmed with this experiment that the particle source emits electrons with opposite spins. So far, this experiment is similar to two opaque crates which look exactly the same and with each crate containing a sphere, for example a blue and a yellow sphere. If we now open one of the crates and find a blue sphere in it, then we also know that the other crate contains a yellow sphere. So what is so interesting about this experiment? And why is entanglement a quantum mechanical phenomenon at all? After all, our two spheres show the same behavior and have nothing in common with quantum mechanics. The decisive point is the superposition principle. Just like for the Stern-Gerlach experiment, here the particle source also emits electrons which are in superposition. That means none of the electrons of a particle pair is in the state of spin up or spin down prior to the measurement. Only by performing a measurement the decision will be made which electron will enter which of the possible two states. And exactly like in the Stern-Gerlach experiment, no one can predict whether a particular electron will enter the state spin up or the state spin down when measured. We can only make statements about the probabilities of the outcome of a measurement, and these are 50% for each of the two states. If we look at our example with the blue and the yellow sphere in the crates again, then we can see the difference compared with classical physics. For our spheres, this would mean that they are neither blue nor yellow before opening the crate. They are in a state of superposition of these two colors. So they would be green at first, and only by opening the crate, which means measuring, they would become blue or yellow. However, if we would open the same crate again and again, then the containing sphere would be sometimes blue and sometimes yellow. Such a behavior is not explainable in classical physics. But what about the prerequisite that the particle source always emits pairs of electrons that have opposite spin? How can this requirement be reconciled with the state of superposition of the electrons prior to a measurement? Let's have a look for that at this table. It displays the possible results if each of the electrons have been in superposition before the measurement. We see that the probabilities for the outcome of the measurement for each individual electron is 50%. The states spin up and spin down each occur 2 times in the column for electron 1. The same applies to electron 2. This is consistent with the results of the experiment. But if we look at the possible combinations of the 2 electrons, represented by the rows of the table, then we notice that the first 2 combinations never occur. The first row implies that both electrons are in the state spin up and the second that both are in the state spin down. But these combinations are contrary to the requirement that the particle source emits only pairs with opposing spins. But the principle of superposition would also allow these combinations. So, does this mean that the superposition principle is wrong? To anticipate the answer, no, it is not wrong. We just haven't applied it correctly. So far we have assumed that the 2 electrons, which form a particle pair, are individually in superposition, so that each individual electron enters this indefinite state of spin up and spin down. But this applies only for non-entangled electrons. With this assumption, we haven't grasped the essentials of the entanglement at all. For a better understanding of quantum entanglement, we will modify our experimental setup now. Namely, we will not measure the 2 electrons at the same time anymore. We achieve this by positioning the particle source in a way that the distances between the detectors and the source are of different sizes. If we now measure the spin of one electron first, then even in a later measurement, the other electron must have the opposing spin. So the result of the second measurement is already certain due to the nature of our particle source. This raises the important question how the second electron knows which spin it has to assume. It just no longer has the choice between the 2 possible states. It must assume the spin which is opposing to the one of the first electron. It therefore looks as if the information about the result of the measurement of the first electron is transmitted in some sort of way to the second electron. And only after the second electron has received this information, then it assumes the appropriate opposite spin. The results of this experiment could be explained with this hypothesis of the exchange of information. And with small modifications in our experimental setup, we have the opportunity to test this hypothesis. Before we do that, we must first make a small excursion into the special theory of relativity. This was published by Albert Einstein in 1905. The important point in the special theory of relativity for us is the statement that no object and no information can travel faster than the speed of light. The special theory of relativity has been checked many times, and all experiments showed that nature actually behaves as it was described in this theory of Einstein. We will now modify our experimental setup by using the fact that information cannot be transferred faster than the speed of light. For this, we install a laser at one of the 2 detectors. This will emit a beam of light exactly when an electron hits the associated detector, so exactly at the moment at which the electron enters one of the 2 possible states of spin. As we see, it is not even possible for the light to bridge the distance from one detector to the other within the short period of time between the 2 measurements. Thus, the information about the result of the measurement of the first electron will never be in time for the measurement of the second electron. Our hypothesis therefore is refuted. An exchange of information between the electrons cannot be the reason why both always assume different spins. The period of time between the measurements, which would have been necessary for such an exchange of information, was simply not large enough in our experiment. In the last years, the entanglement experiments were refined to the point that it could be shown that even 10,000 times the speed of light would not be sufficient to transmit the required information in time from the first particle for the measurement of the second one. The fact that the two electrons always manage to have opposing spins, although an information transfer is impossible, led Albert Einstein describe this as a spooky action at a distance. This choice of words show that Einstein wasn't a big fan of quantum mechanics. However, Einstein wasn't able to create a conclusive alternative to quantum mechanics until the end of his life. Meanwhile, quantum mechanics is one of the most tested physical theories, and all conducted experiments confirm it. But how can we now explain this phenomenon of entanglement? As so often in quantum mechanics, we must abandon everyday experience for this. People tend to regard two spatially separated particles as two independent objects. But quantum mechanics shows that this is not always correct. Two entangled electrons constitute one single, so-called composite system, and thereby the distance between them doesn't matter. They are always one single system. This is a significant difference to classical physics and thus to the everyday experience. The reason for this is the superposition principle. But the two electrons are not each individually for themselves in a state of superposition. So they are not two particles which are in two states of superposition. The composite system as a whole is in superposition. Or in other words, there is only one state which is assumed by both particles together as a whole. If we look at the example with the two spheres in the crates again, then these wouldn't be two individual spheres, although they are spatially separated. This eliminates the need for a transfer of information between the spheres, since it is a compound system. And the opening of one crate, so the measurement of one sphere, is thus always a measurement of the whole system, so of both spheres simultaneously, and not only a measurement of one of the spheres. That also solves our problem from our previous table that non-entangled electrons could both assume spin up or spin down when measured. Since the particle source emits entangled pairs of electrons, the measurement of one of the electrons also immediately determines the state of the other electron. So, by measuring, not one electron assumes the state spin up or spin down and the other the opposing spin, but the whole system assumes the state spin up and spin down, or the state spin down and spin up. So there are only two shared states, spin up and spin down, or spin down and spin up. And it is always necessary to specify two states to describe the state of the composite system. Therefore, no spooky action at a distance, as Einstein called it, is necessary to explain this phenomenon. An action at a distance would only be necessary for an explanation if there would be a distance to bridge between two separated particles. But this is not the case here. Therefore, we should consider the two electrons as one object rather than as two individual particles. The quantum mechanical phenomenon of entanglement thus confronts us with two quite unusual concepts. On the one hand, this is the fact that microscopic objects assume their properties only when measured, and on the other hand, that objects must be considered as a compound system despite their spatial separation. Although this clearly contradicts the everyday experience, all experiments show that quantum mechanics describe the processes of nature correctly.